Thank you for the introduction. I think it's a great workshop. I really enjoyed the talks I attended. I'd like to thank the organizers for inviting me. I'm really glad I have the opportunity to tell you a little bit about the simplex method, or maybe more specifically about randomized pivoting rules for simplex type algorithms. Okay, so a very high-level view of linear programming. So if you studied linear programming in various courses, you probably remember that it was the beginning is a bit tedious. You have a lot of linear equations, linear inequalities, and you have to move from basis to basis. There's a lot of linear algebra. So we're going to gloss over all this and take a more abstract view, but in fact we're going to start with a more geometric view. So, okay, what is linear programming? We want to maximize a linear objective function subject to a collection of linear constraints. The constraints are either equations, equalities, or inequalities. So we can actually ignore equalities, we can easily deal with the equations because we can use them to eliminate a variable. Okay, and then we have a reduced problem with one less variable. So we can do that until all the constraints are actually inequalities. So that's what we will do in the presentation today. Now, each inequality defines a half space. Okay, each inequality, you can view it as a hyperplane in RD, D is the dimension, and the constraint is that the point where we are looking for must lie on a certain side of that hyperplane. So for example, in this case, this is actually a hyperplane, and we require our point to be to the left of that hyperplane. And if we look at all these half spaces, their intersection defines a polyhedron. In this case, it's actually a polytope in the sense that it's bounded, but in general, it doesn't have to be bounded. It might be unbounded. Okay, and we have some objective function, but without loss of generality, we can actually assume that this objective function actually just points up. And then the problem boils down to finding the highest point in a polyhedron. And in this specific case, this is the solution. This is the highest point in this polyhedron. Okay, that's linear programming, right? Now, what is the simplex algorithm? The simplex algorithm says the following. Start at some vertex of the polytope, of polyhedron, and move up from vertex to vertex along edges until you reach the top. Okay, that's a very high-level view of the simplex method, and there are a lot of details to fill in. Right, the very first detail that is missing, how do we find the initial vertex? Okay, that's already a non-trivial part. Okay, this is essentially done by solving a different linear program for which we do know initial vertex. Okay, but so this can be done. Now, the next thing I should tell you, so what is a vertex and what is an edge of the polytope? Okay, so a vertex is sort of an extreme point of the polytope, the polyhedron, or more formally, it's actually the intersection of the polytope with the hyperplane. Okay, so each one of these vertices, there is a hyperplane that intersects the polyhedron only in that place. Okay, and that's one of the equivalent definitions of a vertex. Now, what is an edge? An edge is a one-dimensional intersection of the polyhedron with a hyperplane. So you can, if you look, for example, at this edge, you can see there is a hyperplane that intersects the polyhedron exactly in this edge. Okay, so that's the geometric definitions of vertices and edges. Okay, what other, are there any other details I have to tell you about this, about the simplex method to make it an algorithm? What do you think? So did what I tell you right now is a well-specified algorithm?
You need to find out edges coming from it.
Yeah, so it's sort of a family of algorithms because I didn't tell you which edge to take if there is more than one possibility. Okay, for example, when we're here, there are actually two edges that go up. Right? We decided to go right, but equally well, we could have decided to go left. Okay, so this is called the pivoting rule, which specifies if you're at a given vertex and there are several edges that go up, which one of these edges to choose. Okay, and there are a lot of, we could spend hours about talking about various pivoting rules, their advantages and disadvantages. Okay. Now, the obvious upper bound on the number of steps of the simplex algorithm is the number of vertices of the polyhedron, but unfortunately, the number of vertices might be exponential in the dimension. So, at least if we don't do anything clever, the algorithm we get might be exponential. Okay, that's something we'll have to face. Okay, we'll try to get bounds on the number of steps, which are much better than the number of vertices, the potential number of vertices of the polytope. Okay. Any questions about this very high-level introduction?
You could also cycle, right?
Okay, so cycling belongs to one of the things I'll call annoyances in the next slide. So cycling only happens if you have degeneracy. Degeneracy means, so this is a polytope in 3 dimensions. And note that this is a well-behaved polytope because each vertex is exactly on the intersection of 3 hyperplanes. So there are cases in which, so a vertex can possibly be on more than D facets, D hyperplanes. For example, if you take the pyramids in Egypt, right? So the top vertex is, so this is a 3-dimensional object, but the top vertex is actually on the intersection of 4 hyperplanes. And this causes all sorts of problems, but they are not really serious problems. They are just annoying problems because there are known techniques to deal with them. And as I'll say in a minute, this is exactly the sort of details I don't want to talk about today because there are much more important things we need to discuss. Okay. Yeah. So one other thing is that okay, so maybe I'll say that. So there is a correspondence between vertices and bases, right? So a base would be the set of inequalities that define the vertex. Okay, and each vertex is defined by the intersection of D hyperplanes, where D is the dimension. Now, sometimes this defining basis is not unique. And this is what gives rise to the possibility of cycling. In cycling, you're essentially not moving. You're staying in the same vertex, but you are changing bases. Okay, but yeah. Okay, any other questions? Okay, so some preliminary notation and discussion for what I'm going to talk about today. Our view will be fairly abstract, and by abstract here I mean two things. So the first thing is that I will actually ignore all the algebraic computations, and I will view things from a slightly higher point of view. There is actually a more profound meaning of this abstract, which I'll repeat what I'm saying now at the very end. Since we are using essentially abstract terminology, everything we are going to say will apply not only to linear programming, but actually to a wider class of problems. Okay, and again, I don't want to confuse you with the details, but just bear in mind that the fact that we are doing things, so to speak, abstractly, means that we can actually generalize all the results to more general problems. Okay. The second remark is that we'll actually gloss over some annoyances, okay, such as cycling, right, or degeneracy or things like that. And I'll mention, whenever I'm glossing over something, I'll try to mention it. If I don't, try to catch me, and okay, and then I'll say, yeah, okay, that's a problem, we have to solve it, but not in this talk. Okay, just to fix the notation, we let n be the number of inequalities, d is the number of variables, or if you like, the dimension of the problem. And since we are in a parameterized complexity workshop, let me say that we've essentially view d as the parameter. Okay, we think of d as potentially being much smaller than n, and this is consistent with the point of view used by the computational geometry community. Usually, they are considering problems in low dimensions. Okay, we have lots of inequalities, but the dimension might be small, might be even just 3 or 4, right, or 6, 10. Okay, so we let h denote a collection of inequalities. And now h, the letter h was chosen because to remind us that an inequality just defines a half space. Okay, so this is h, and lowercase h would be a specific inequality. Now, given a collection of inequalities h, we have a linear program which says maximize the objective function. For us, think of the objective function as always being up. So maximize the objective function subject to the constraints in the collection x, and the solution would be a vertex. Okay, which we denote by v of h. Now, another slight annoyance is that the solution is sometimes, if the problem is degenerate, maybe the solution is not obtained in a unique vertex. Maybe there are several vertices that achieve the same value. Okay, so we will have to break tie and define Vx to be one of these carefully chosen solutions, and this goes into what I call the annoyances. Okay, so just to tell you what we are doing, usually we'll just take among all the optimal solutions, so it's well known that there is always an optimal solution which is a vertex, and among all the optimal vertices we can take, for example, the lexicographically smallest one. This is sort of a rule that would solve this annoyance. Okay, so we denote by v of h the optimal solution, and I'll actually use both notations depending on whether I need to whether I have a lot of things to write in the line, or whether I want to emphasize to make it clear, easier to read. So these are equivalent, so they will appear interchangingly. And okay, so in addition to finding the optimal solution is a vertex, we'll also be interested in the basis which defines this solution. We'll denote it by basis v of h. This is the set of d inequalities that determine v of h. Now, note that this is not the only thing that we require from the basis. So essentially, if we have the basis, we can compute v just by solving a system of d linear equations. But the other property that we require from a basis is the following. So if we let's spend a minute on this equation, because this is important for the rest of the talk. So what this means is that okay, so we want to find the optimum subject to a collection of constraints, and the problem is maximization. So what happens if we have less constraints? So if we take some of the constraints, so if we take a subset of h, and we look for the optimum, what happens to the optimum? So since we have less constraints, maybe the optimum is larger. right? Now, what I want to say here is that if I just look at the D constraints that appear in the basis of V of H, so this defines a much smaller optimization problem, and I claim that the optimum of this problem is actually equal to the optimum of the original problem. This essentially means that the inequalities in the basis are really the important inequalities. If we impose them, all the rest are actually not really important. They are redundant.
Is it correct to see it as a kernel of your problem?
Yeah, in a sense, yes. So, but that's also the solution we want to find, right? Once we have the basis, we have the vertex. Okay, and essentially also the other way around. If we have a vertex, we can easily find the basis. Okay. Any other questions here?
Is it obvious that there always exists a basis that is a subset of H?
Yeah, okay. So this is sort of, it follows from the basic properties of linear programming, which I will not repeat. Sort of intuitively, okay, if there is no degeneracy, then the basis is just the set of hyperplanes that contain the vertex. Okay, if there are degeneracies, then we must be a little bit more careful. Okay.
Is it easy to update this basis, or is this difficult?
So if there's no degeneracy, it's very easy to. This is just the constraints which are tight, the constraints which the vertex satisfies with equality. Okay, but the algorithm would actually most of the algorithms we will see will not just output a vertex; they will at the same time compute the basis. And that would be important for the working of the algorithm. Okay, now I have to admit right from the start, so I gave you this nice geometric view of the simplex algorithm in which we move from a vertex to a vertex. Actually, what we will do will not quite do that. We'll essentially be considering dual simplex algorithms, which essentially apply the simplex algorithm on the dual linear program. Okay, and I don't want to spend too much time on explaining what this is. Maybe we'll see what we are doing, and then I can tell you, I'll try to explain that later on. Okay. Any other clarifying questions? Okay, so let's start with a really nice algorithm of Seidel from 1991. Okay, so we have a set H of n inequalities in D variables, and we want to find the optimal solution, V of H. Okay, an optimal vertex. So in this algorithm, we still don't look at bases, and this is why we'll be able to improve this algorithm later if we also consider bases during the operation of the algorithm, not just solutions. Okay, so all the algorithm would fit here, so it cannot be too complicated, right? So this is what Seidel bravely does. So we choose a random inequality, a little h from capital H. Now, I should also say that essentially all algorithms will be randomized. Okay, so we choose a random inequality, and we ignore it. Right? Seems dangerous, but we do it. Right? Okay, and we solve recursively the problem without this inequality. Okay, and we get the optimal solution of this problem, which in our notation is V of H minus H. Okay, what do we do next? What do you think? So we removed an inequality, we got a solution. What's the natural thing to do? So to check if this solution satisfies the inequality we removed, right? So we check if VH minus H satisfies H. If it does, then great, we are done, right? This is also the optimal solution of the whole problem. Okay, what happens otherwise?
We return or fix the solution.
Yeah, so what can we infer if this is not satisfied? H is, yeah, very nice. H is important. The optimal solution must satisfy H with equality. We cannot ignore it. Okay, so that's great. So we know we found one of the D constraints that define the solution. Okay, now what Seidel does is actually explicitly uses this equality to eliminate one of the variables. And now we have a problem with a smaller dimension, and we recurse. Okay? So otherwise, turn H into an equality, use it to eliminate a variable, and solve the reduced problem recursively. Okay? That's almost the whole algorithm. Yeah?
What happens if the inequality you removed caused the problem to be unbounded, or is that one of the inconveniences?
Yeah, this is one of the, what I call the annoyances. And you're right in the sense that we definitely have to worry about this, right? Otherwise, it's not a complete algorithm. But I don't want to spend time on these details because they are not the main details. There are standard ways of dealing with that. Okay, so and I'll mention a few other things which I'm glossing over. You're invited to, but at least I think you'll see the main gist of the algorithm. Then there are small, tedious, not too tedious things to finish. Okay. Now, let's analyze this algorithm. Okay? So, what do we want to show? We want to show, not that, so we chose a random inequality, we removed it, and if we were lucky, this was not an important inequality, and we actually got a solution of our problem. Right? But how many important inequalities are there? At most D, right? If we choose an inequality which is not in the basis, then it didn't matter. When we removed it, the solution didn't change. Okay? So what's the probability that we need to do a second recursive call? It's only D over N, which is great. So so we always think of N as being larger than D, right? Otherwise, the problem is not well defined, and usually N is much larger than D. Then the probability that we do a recursive call is fairly small. Okay, and this naturally leads to the following recurrence relation. So FDN is sort of the expected running time of the algorithm. Okay, so to solve a problem with in dimension D n inequalities, we first remove an inequality, right? So now the first recursive call is bounded by this expression, and then only with probability D over N, we have to do a second recursive call. But in this second recursive call, the dimension decreased by 1, and the number of constraints decreased by 1. Okay. Okay, so this is the recurrence relation we need to solve. Now, what's the solution of this recurrence relation? It's actually easy to see that f and d is actually upper bounded by d factorial times n. And just 1 second. And here is the proof by induction, right? So if we assume that fd n minus 1 is at most d factorial n minus 1, and fd minus 1 n minus 1 is at most d minus 1 factorial n minus 1, then when we multiply this by d over n, then d times d minus 1 factorial, that's exactly d factorial. N minus 1 over n, this is less than 1. So we have d factorial times n minus 1 plus 1, which is exactly d factorial times n. Okay, that's the proof of this upper bound by induction. Yeah, there was a question?
Yeah. Just one quick question. When you say you're converting H into an equality, is it by adding a slack variable or you just change the sign?
No. So what is the inequality? So we get an equality, right? Now we can take any of the variables appearing in this equality with a non-zero coefficient, and just say, okay, now this variable is not really a free variable. It's a linear function of all the other variables. Okay, now we can just remove this variable from our program. We can just, whenever it appears, we replace it by this linear combination of all the other variables, and everything stays linear. Okay? Okay, so we saw our first algorithm. It's already linear in n, which is great, right? So this is a very nice fixed parameter algorithm, right? So it's the dependence on the parameter is a bit high, d factorial, but it's linear in n, and this is only our first attempt, and it was an extremely simple algorithm. Okay, now which details did I gloss over here? So what is the... Hmm? No, okay. This is the magic of recursion, right? But when we use recursion, there is something we need to specify, and this is what? Yeah, what is the basic case of the recursion, right? So what would be the basic case here? So one of the basic cases is in which the dimension drops to 1. Okay, now what happens when the dimension drops to 1? When dimension drops to 1, this is really simple. We just have to find the minimum and the maximum, and then see if the problem is feasible, and if so, we know which end of this interval is optimal. Okay, so but this is not everything, because we may reach a condition in which the dimension did not decrease, but the number of inequalities decreased until... So one other base case we need to deal with is what happens with n equals d. Right? If n equals d, then there is a unique... So if we turn all the inequalities to equalities, we have a... Okay, if they are linearly independent, we get a unique solution. Okay, but this is not necessarily... we still have the possibility that the problem is actually unbounded, right? Maybe we have a solution, but this is not really constraining. We can actually, so if we have just d inequalities, we essentially have a cone. And now the question is, in which direction does this cone point to, right? Either we have an optimum or the problem is unbounded, okay? But this is, again, one of the annoyances. So it's not difficult to deal with that, but we will not do that because it will take too much time from other things we want to discuss. But the main things, this is the main idea of the algorithm. Yeah, go ahead.
Not feasible, doesn't it mean that the entire thing is not feasible?
Yeah, so maybe the whole thing is not feasible. Yeah, right, that's a good observation. So if we look at a subset of the constraints and it's not feasible, then we know that the whole thing is not feasible. That's great. But even if the whole problem is bounded, if we remove some constraints, maybe the sub-problem is unbounded. Okay, but there are various ways of dealing with that. So either just see that everything we say still holds if we allow. So if the thing is unbounded, we can view the solution as an optimal ray. But I don't want to get into it. Or we can introduce upper bounds and lower bounds, which would mean that the problem would always be bounded. These are just. I think they are not as beautiful as the details are not as beautiful and as important as the main details I'm trying to convey in this talk. Yeah.
What's wrong in inequality to equality? So, like, you need to produce some like variables. So, you increase the number of variables and decrease it, or you just turn it into an inequality and hope that it will go into equality.
Yeah. Okay. So I claim that if this happens, then okay. So if this doesn't happen, then we know that H is important. But if H is important, then it's not hard to see that H is actually should be satisfied with equality. Okay, so we don't need to introduce any slack variable. Okay, but this again is one of the basic properties of linear programming. But if you think about it, it's intuitively fairly obvious, and it's not hard to produce a proof. Okay, any other questions? Okay, so here is a small example in 2 dimensions. Okay, suppose that we are, these are the constraints. So each constraint is an inequality, or alternatively a hyperplane, in which case in 2 dimensions that's a line, and this indicates the direction. So we want our point to be below this line, to the left of this line, and so on. And we want the highest point subject to all these constraints. Right? So if you think about it, if you look at this picture, you see that this is actually the feasibility region. This small triangle is the set of all points that satisfy all these 5 constraints. Okay, and these are the vertices of this feasibility region. Now, if we were running a simplex algorithm, we would start with one of these vertices and then climb up until we got to the top. Okay, but as I said, we're actually doing dual simplex. So we're actually not working on vertices of the polytope. We're actually working on points which correspond to vertices of the dual polytope. But doesn't really matter. But let's see what Zeidel's algorithm is doing. So we choose a random inequality and remove it. Now, note that if we, so which inequalities here are important? Only these 2 inequalities are important, right? If we, this one defines the feasibility region, but it's actually not important. It's also not important. The only important inequalities are the inequalities that define the optimal vertex. Okay, so if we remove this, so if we remove this inequality, nothing happens. The first recursive call would actually return the optimal solution. Okay, similarly, if we remove this high inequality, we would immediately get the correct solution. And similarly for this one. Now, let's see what happens if we remove, for example, this inequality. Okay, so what would happen to the feasibility region? Can you see? Well, yeah, so there are points here that would actually want to go upward, but they cannot because they hit this boundary. If we remove this inequality, this would actually be the feasibility region, right? So at this point is no longer a vertex, so these are the new vertices, and this is now the optimal solution. Okay, this is what we will get by the recursive call to the algorithm. Okay, so so this is what the first recursive call returned. Now we check. Is the vertex return satisfy the inequality removed? The answer is no. What do we infer from that? That the solution is on this line. Okay, now we are down to a 1-dimensional problem. Okay, so we convert everything. So this inequality would now say that the point is to the left of this point on the line. Okay, and once we are down to 1 dimension, then we solve it using a base algorithm. Okay, and similarly, if we remove this inequality, the solution would now be this one, and it does not satisfy this inequality. Now we know that we need to make this inequality into inequality. Okay, so this is Zeidel's algorithm. Any questions? Okay, luckily in this example we avoided all the annoyances, okay, but they are there. Okay, next item on our agenda is a reduction by Clarkson, which shows that we can essentially concentrate in the case in which the number of inequalities is not more than quadratic in the number of variables in the dimension. Okay? And Clarkson gave two algorithms. The first algorithm is the following. So let me explain how this should be interpreted. Suppose that we already have a linear programming algorithm whose complexity is bounded by f. Okay, f is a function of d and n, the number of variables. We just saw our first bound, d factorial times n, right? But take any algorithm. So it's a sort of a black box reduction. It takes a linear programming algorithm and turns it into a slightly better linear programming algorithm, or essentially it turns it into an algorithm that would only call this box when n is at most quadratic. Okay? So if we have such an algorithm, it would convert it into algorithm which we'll call it alg1, which is bounded by the following running time. And the nice thing about this algorithm is that the expected running time of this algorithm would be ordered d squared times n plus 2d f d 3d root n. Now, it doesn't really, well, the exact form here doesn't really matter, but that's what the first reduction does. Now, what does the second reduction does? This is it's similar to the first reduction, but the nice thing is that now we are really down to only a quadratic number of inequalities. In exchange, the additive term here is not d squared n, it's actually d squared n log n. Okay, it's slightly higher. Okay, now what can we do with these two reductions? What would be a natural thing to do? To combine them, right? So run the first reduction on the algorithm you obtained by the second reduction, right? And if you do that, you'll get something like this, which simplifies to this. So the nice thing is that we get the best of both worlds. Essentially, we only have d squared n, and we only call the base algorithm when n is at most 6 d squared. Okay? And we also have this intermediate term, but this is actually always dominated by either this term or this term, so it doesn't really matter. Now, what happens if we apply these reductions to Zeidel's algorithm? Then we get the following bound. So if we just plug d factorial n into f, we get this, and after a simple simplification, we get essentially the following: d squared n plus d factorial, not quite d plus 6 factorial. Okay, now this is great, right? So we've separated, we got an additive result, right? So these are our parameter, the dependence is only of the form d factorial, and it's not multiplied by anything related to n. Okay, this is even if we just use the basic algorithm of Zeidel, using this reduction, which we'll explain in a second. Okay, now we'll actually see in a minute, towards the end of the talk, a much faster algorithm, an algorithm that is much faster than Zeidel, and the ultimate result that we'll obtain is the following. So instead of having d factorial, we have something which is more than exponential. We'll have something which is sub-exponential. 2 to the order root d log d. Okay? And this is essentially the fastest known algorithm as a function of d. Okay. So what we will do is we'll consider the second reduction. Okay, we don't have time for both reductions. The second one is more interesting, and note that even on its own, it essentially would give us this result, except that we would have a log n here. And it could be avoided if we also use the first one, but and the details of the first one are fairly similar to the details of the first one. It would be, we don't have time to cover both of them, so the second one is the one I chose. Okay, any questions so far? Yeah.
Are there any evidences how optimal is some exponential algorithm? So can it be even returning to polynomial dependence on D? Or there is some...
Okay, so that's one of the things we need to discuss. Note that actually linear programming is a polynomial problem. Okay, so there is a polynomial time algorithm. So everything can be done in time which is polynomial in D and N. And actually not only D and N, and also the bit complexity of the problem. So linear programming is polynomial, but it's not known to be strongly polynomial, right? So the running time would depend on how large the coefficients in the problem are. So in that sense, but if you apply that algorithm, the ellipsoid or some interior point algorithms, you get some running time which is polynomial in D and N and the bit size. Okay. Now, it's a major open problem whether linear programming is strongly polynomial. Strongly polynomial would mean that you have something which is polynomial in D and N, right? Now, whether we can actually get something which is linear in N and still polynomial in D, that's an even harder problem, right? So we don't know.
So this is a strongly polynomial. I mean, this has this number of arithmetic operations, and that doesn't depend on the bit size.
It doesn't depend on the bit size, assuming that each operation takes constant time, right? This is the standard RAM model. And we are not abusing this model in the sense that we don't generate huge numbers. Everything we are doing is solving linear equations, which is known to be strongly polynomial. Okay, any more questions? Okay. So we have about 10 minutes, I think, for the first part. Let's start with this, with Clarkson's second algorithm. And this is also a really nice algorithm, so I'm really glad I got to speak about results I really like. So I hope you'll also enjoy them. So Clarkson says the following. So we have a collection of n inequalities, and what we do is we weigh them. We give a weight to each inequality. The weight seems to indicate how important we think this inequality is. So initially, we don't know anything, so we give each inequality a weight of 1. Eventually, we want our D inequality, the D essential inequalities, to have very, very high weight, so we can actually tell them apart from all the others. Okay. So it's a slightly more complicated algorithm. It still fits on a slide. So what Clarkson is saying, repeat the following step. So choose a random subset of H of size 6D squared. Okay, so we choose a random subset of quadratic size. Now, okay, but we choose the inequalities to this random subset with probability which is proportional to their weight. So if we seem to think that this inequality is important, we sample it with a higher probability. Okay? Now, what do we do with this random subset? Of course, we solve it. Okay? Now, we solve it using the Bayes algorithm, because this is a call to the Bayes algorithm where the number of inequalities is at most quadratic in the dimension. Okay? And we get some solution. Okay, now, of course, if this solution satisfies all the inequalities, that's we are really lucky, and then we are done, right? But this is not likely to happen in the first iterations of the algorithms. So what we do is we define the set V to be the set of all inequalities in H which are violated by V. Okay, uppercase V stands for violators. Okay, now what do we hope that would happen? We hope that this set V is not too large, right? If V is huge, then it seems that we may not have gained much from this iteration. Okay, but so this is the best case scenario. If V is empty, we found a solution. Otherwise, we see what is the weight of the violation set. Okay, and if it's at most 1/3D times the weight of the total weight of all the inequalities. So W was defined for a single inequality, but W of a subset is just the sum of the W of each inequality. So if the total weight of the violet inequalities is not too large, we double their weight. Okay, it would have been natural to say that in each iteration just double the weight of all the inequalities which are violated, but this things could go a little bit out of control. We don't want to increase the weights too much, so we only do that if the iteration is what we call successful, if this condition is satisfied, and we'll see in a minute that this happens with high probability. So in most iterations, we update the weights. Okay, and that's it, we repeat. Until, luckily, we choose a random subset which includes the D essential inequalities, and then we are done. Okay, so note that the algorithm would terminate in any case, because even if we blindly choose, the expected number of iterations is finite in any case, because even if we blindly choose random inequalities, eventually we'll be lucky, and it's not my laptop. So okay, but what we hope would happen is that since we are increasing the weight, therefore the probability of choosing inequalities that were violated many times, we hope that we give a higher probability of choosing really the important inequalities. Okay, and the essential lemma in the proof, in the analysis of the algorithm, is the following sampling lemma, which says the following. So here I'm just repeating the scenario of what we had. So let H be a multiset. Okay, so one thing I have to say, so instead of giving weight to an item, now note that our weights were actually all integral, right? Because we started in 1, we always multiplied by 2. So in fact, there are always powers of 2. But so instead of saying that an inequality has weight 16, I'm just thinking of it as having 16 copies of that inequality, okay? That's more convenient for the analysis. For the running of time of the algorithm, of course, we don't want to duplicate the inequalities. I mean, there's no point in doing that, but for the analysis, we can actually think that there are no weights, we just duplicate the inequalities. And then we just sample uniformly. So n is now not the number of original inequalities, this is how many inequalities we have at the start of a certain iteration. Okay, so let H be a multiset of n inequalities in D variables. We choose a random subset of size R. We find a solution subject to R. And now we look at all the set of inequalities in H which are violated by R. And now we claim the following, that the expected size of V is quite small. And more specifically, it's n minus R times D over R plus 1. Okay? Now, this is... Okay, so... yeah, we'll see. It has some flavor similar to the inequality we used in the analysis of Zeidel's algorithm. Here it's slightly more intricate. So that's the claim of the sampling lemma. Is the claim clear? Okay, so I only have something like 2 minutes, so let me... actually, maybe that would be a good time to stop the first and take a break, and then we'll continue the proof after the break. So there'll be some suspense. Okay.